welcome to Atomic Trends part 1. In this part, we're going to look at atomic radii and ionic radii. The atomic radii of an atom is defined as, really, if you're kind of just looking at the radius of an atom, which is a difficult thing to measure since the electron cloud can be a little bit fuzzy on the edges. So this is the distance between the nucleus of an atom and the outside of the electron cloud. So it's really the same definition you're used to hearing about in geometry class, but in order to measure this, they typically take two identical atoms and put them right next to each other and then measure their distance measure the distance between the nuclei, because that's a little bit easier to measure. For your purposes, what you need to understand is this is a description of atomic size. Remember, atoms are neutral. These species have not gained or lost electrons. So essentially this trend has to do with atomic size. It's in a unit of something called a picometer, which is 10 to the negative 12th meters. So obviously small, because atoms are small. So we can actually look up values for atomic radii. If you go to reference table S, we can find sodium, potassium, etc. So we're going to start at sodium, and we're going to go over to the atomic radii column, which is the last column on there. We've got 160 picometers for sodium. Magnesium is 140 picometers. Aluminum is 124 picometers. Silicone is 114 picometers. And phosphorus is 109 picometers. So what we're seeing is, as we go from left to right on the periodic table, it's important to note that we have 11 protons, 11 electrons, 12 protons, 12 electrons, 13 protons, 13 electrons, 14 protons, 14 electrons, and 15 protons, 15 electrons. So as we're going from left to right, we're actually increasing in the number of protons and electrons in the atom, yet the size of the atom is getting smaller. So you can actually look this trend up. It's not like the trend itself is something you need to memorize, but it is very important to understand why this occurs, and this is something that you need to know. As you go from left to right on the periodic table, this actually relates just to that effective nuclear charge that we talked about. So within a period, as we go from left to right, as we go that way, our number of protons is increasing. In other words, we have increasing nuclear charge. However, the number of PELs stays the same. So within, for example, period 4 on the periodic table, as you go from left to right, you're getting more and more protons, which are pulling in on the electrons with a lot more strength. Because the number of PELs are the same, you essentially get a stronger effective nuclear charge, which kind of sucks those rings in a little bit tighter. So thus, even though you have more stuff in the atom, because electrons are really, really lightweight, they're just really bossed around by those protons in the middle. So they get sucked in a little bit tighter, and we have a decreasing atomic radius as we go from left to right. And you actually did this graph before, so just to kind of review with you what this looks like. You can look right here, we got lithium, lithium. As we go across the periodic table, you can see where we end up at fluorine. Our next one that's a little bit bigger is sodium. Go across the periodic table, you end up down at chlorine. And then looking at our last row that's on here, we're going from potassium over to bromine. So this does repeat periodically on the periodic table. So again, this has a lot to do with effective nuclear charge. So I just wanted to kind of review this concept with you. So if you put your little eyes on potassium versus chlorine, okay? So potassium versus bromine. So potassium is the configuration 2, 8, Potassium's effective nuclear charge, remember, is protons minus kernel electrons. So this is going to be 19 minus 2, 4, 6, 8, 10, 12, 14, 16, 18. So what this actually means is the nucleus has a positive 1 effective charge on the valence shell. Compare this to bromine. So if we fill in bromine's electrons, we go 2, 8, 18, 7. That's a lot of electrons. So our effective charge for bromine is our 35 protons minus our kernel electrons, which is 2 plus 8 plus 18, so minus 28. The difference between those is 7. So this is much stronger and pulls in electrons tighter. Therefore, bromine is smaller. So that this effective nuclear charge is very important with ideas such as bonding, and it also plays into ideas such as atomic size. You do not need to know how to calculate effective nuclear charge, but you need to be able to understand why this trend occurs. So a common thing you might be asked is to describe in terms of atomic structure why the radius of a potassium atom is greater than that of a bromine atom, even though bromine has more electrons. And the reason for this is potassium has a lower, and you can use the word effective, but you don't have to, nuclear charge. Or bromine has a higher nuclear charge, either one. So you can kind of go either way on that. Again, whether or not you use the word effective is up to you, but they do have the same number of principal energy levels. So because of that increased effective nuclear charge, the principal energy levels are being pulled in tighter. So as we look down a group, this actually makes a ton more sense and is a really simple one to understand, because what's going to happen down a group is we're going to get an increasing number of PELs. So we're going to start by looking at lithium, which is number 3. Lithium's got an atomic radius of 130 picometers. Next, we're going to go to sodium. Now, lithium has 2 rings of electrons. Sodium has 3 rings of electrons. So sodium has a radii of 160 picometers. Potassium has 4 rings of electrons. So look down at potassium, we get 200 picometers. By the time we get way down to rubidium, rubidium has 1, 2, 3, 4, I believe 5. Trying to remember offhand, I don't want to screw this up. Yep, we got 5 rings of electrons. They're not really all out of whack and out of shape like that, but you know, I'm not the drawer. So rubidium, 215 picometers. So what we see here is as we go down a group, we go from 3 PELs to 4 PELs to 5 PELs to 6, 3, 4. Oh, sorry. All that work to not make a mistake on the other side. Sorry, lithium's 2, sodium's 3, 4, and 5. So what we can see very clearly with this trend is as we go from top to bottom on the periodic table, atomic radii will increase, and this is due to an increasing number of principal energy levels. I really liked this graphic. I just think it's kind of nice where you can see like your biggest atom is going to be cesium, because as we go down, we're going to have an increasing atomic radii. And as we actually go this way, we're going to have an increasing atomic radii. So I think this is kind of a nice graphic because you can see, hey, when you're way up over this top corner, you have very few PELs and you have a really tight, pulled in, small atomic radius. We also need to be able to compare neutral atoms to their ions. So sodium has the configuration 2, 4, as an atom. What happens to sodium is it loses that electron and becomes just 2-8. So effectively this whole outside ring here kind of goes away. So what we see, and you cannot look up, you don't have in your reference table these values right here. That's what's called an ionic radius. But you don't need to know that exact value. All you need to know is that if the atomic radius of sodium is 190 and it loses an electron and that whole PEL goes away, we expect that that atom, or the ion, will be smaller than the atom. On the other end of this, if we're looking at fluorine, for example, we're going to have the configuration 2-7, and fluorine's ion has the configuration 2-8. It gained an electron. So again, we see the atomic radii as being 57. The 95 is our ionic radii. You can't look that up, but you don't need to know. You don't need to know it. What we do know, however, is that because we have more electrons on here, we actually now have a situation where that extra electron causes repulsion. So what's happening is fluorine's having a hard time pulling on that outside ring of electrons. So because of gaining an electron, there's more repulsion between all the electrons, and fluorine kind of swells up essentially and gets a little bit bigger. And again, as I mentioned before, atomic radii are on table S. Ionic radii are not. You don't need to know these numbers. I have seen them give them to you in problems, so you can, answer questions with them. You just need to understand this trend. Any positive ion is going to be smaller than the atom it came from. Any negative ion is going to be larger than the atom it came from. So positives are smaller because they lost. Negatives are bigger because they gained. It's actually something that makes sense. Next, we'll talk about trends in electron activity and ionization energy in the part 2 video.